Hello everyone, my name is Nathan Rodriguez-Lynn and welcome back to my YouTube channel. So last week we went through large language models and attention and transformers, and today we will be going over reinforcement learning in GPT, InstructGPT, and ChatGPT using some resources. The first one being reinforcement learning from scratch by Graphics in 5 Minutes. Reinforcement learning through human feedback explained by Code Emporium. Reinforcement learning from scratch, reinforcement learning AlphaGo, and reinforcement learning ChatGPT and RLHF by Graphics in 5 Minutes. And then the article on OpenAI titled Aligning Language Models to Follow Instructions. So let's just get right into it. So reinforcement learning from human feedback, or RLHF, has emerged as a turning point process of tuning large language models to human values and human tastes. In contrast to the traditional supervised learning from massive amounts of static text corpora, RLHF allows models to be trained through iterative human feedback. The process is particularly valuable where ethical considerations, factuality, and user happiness matter the most. Through the use of reinforcement learning principles, RLHF guarantees not only that the responses generated by AI are coherent, but also that they are aligned with human values regarding safety, usefulness, and ethical suitability. The RLHF model is based on two fundamental datasets, the prompt dataset and the preference dataset. The prompt dataset is comprised of all the various user inputs that the AI model will be asked to respond to, and the preference dataset is filled with many potential responses ranked by human raters. From these rankings, the model learns which kinds of responses are preferred. This allows for an iterative refinement process in which human raters guide the AI towards producing an increasingly desired and contextually appropriate output. Instead of relying on fixed corpora, the model has the flexibility to calibrate its output dynamically based on human feedback, thus reducing biases and increasing the reliability over time. To further improve the AI in responding based on human feedback, RLHF employs a reward network. The reward network is responsible for predicting the score that a human would assign to a response, effectively simulating the process of regular scoring. The reward network is typically an LLM with the final layer substituted with a scalar output, which is the response quality score. This enables the system to scale well, supporting continuous improvement without requiring human evolution for every single response. With the automation of the reward mechanism, RLHF enhances scalability while maintaining the benefits of human-in-the-loop review. This not only optimizes model performance, but also guarantees responses are contextually appropriate and compliant with ethical guidelines. One of the largest challenges in rolling out RLHF is getting high-quality training data for the reward model. In contrast to supervised learning, where there is a wealth of labeled text data, human feedback for RLHF is relatively scarce and costly to produce. Human annotators may also introduce subjective biases, and this can render the training data inconsistent. These issues have the potential to impact the consistency of the reward model and therefore necessitate the application of techniques such as multi-annotator aggregation and bias correction methods. Moreover, the cost and scalability of human feedback remains a significant issue, and researchers have therefore sought to explore semi-supervised and AI-assisted annotation methods in order to counteract the expense of manual labeling. For optimal tuning of the reinforcement learning process, RLHF tends to use policy gradient methods with proximal policy optimization, or PPO, being a preference option. PPO boasts the ability to balance exploration and exploitation to ensure that the model enhances its responses while exploring new methods. Among the core reasons why PPO is most preferred is its ability to prevent drastic policy updates, whose emergence makes learning unstable. By constraining updates to a predefined range, PPO allows for stable and efficient fine-tuning of LLMs such that they can more closely align with human feedback over several training iterations. This makes it particularly well-suited for applications requiring incremental improvement rather than extreme model behavior change. At a broader scale of AI training, exploration is essential not to get stuck with local optima. Agents who are trained via reinforcement learning struggle with settling into suboptimal strategies too quickly if they exploit too much given knowledge. Randomness is incorporated into the training process, specifically in an attempt to dissuade the agent from remaining within predefined parameters and urge it to consider other options. Techniques such as entropy regularization and epsilon greedy methods act to balance exploitation and exploration and ultimately yield more stable decision-making. The rule is very suitable in advanced environments where solutions of the optimal type are not obvious and must be subjected to lengthy trial and error procedures to find them. Deep reinforcement learning has been extremely capable, particularly in learning to play video games using raw pixel input only. And neural networks are able to take high-dimensional visual data and learn useful features without being specifically programmed. This feature has been made evident through applications such as deep Q networks, where AI agents learn to play Atari games at superhuman levels. By analyzing game frames and correlating actions to rewards, these models learn progressively sophisticated strategies that are better than human insight. The efficacy of this approach proves that the potential of reinforcement learning, where pattern recognition and strategic choices are the most critical. One of the best illustrations of reinforcement learning capability is the game Go, where memorizing past games become insufficient after opening moves. Due to the immense complexity of the game, no two games are ever duplicable, requiring players and even AI agents to devise adaptive strategies over mere memorization. This requirement made DeepMind's AlphaGo all the more remarkable. And if you remember, AlphaGo is something that we have covered in previous videos. And in addition to mimicking human intelligence, AlphaGo combines supervised learning from master games with reinforcement learning playing against itself. By continuously playing against itself, AlphaGo developed its strategy, discovering new moves and tactics that even the world's best human players were not aware of. This process of self-improvement allowed AlphaGo to surpass human performance, showing the power of reinforcement learning in acquiring very complex decision-making tasks. Though such achievements have been made, there are criticisms of the efficiency of reinforcement learning by others like Jan LeCun. In LeCun's opinion, reinforcement learning is sample inefficient by design, and acquisition of useful policies requires an unimaginably huge number of experiences. Other techniques, for example, learning world representations by observing, he suggests. According to him, AI systems must first develop a solid foundation of understanding the world by self-supervised learning and model predictive control later for making more informed decisions. LeCun recommends that reinforcement learning should be used only when predictive models fail and as a correction mechanism rather than being the primary learning strategy. His perspective emphasizes the need for more efficient learning structures that minimize the computational and data needs of reinforcement learning-based approaches. The evolution of reinforcement learning, particularly towards the direction of RLHF, offers both its potential and its limitation. By integrating human feedback into the process cycle, AI systems can be more susceptible to being in adherence to ethical standards and user needs. However, human-in-the-loop monitoring scalability is still a bottleneck, and therefore better methods for feedback retrieval must be attained. In addition, although reinforcement learning has demonstrated impressive performance in domains such as gaming and language modeling, its inefficiencies make it questionable for wider applicability. As AI continues to evolve, the most pragmatic approach may be a hybrid approach that combines reinforcement learning with other machine learning methods. The long-term goal does not shift, creating AI systems that are not only capable, but also share human values and can make smart and ethical decisions in a variety of real-world tasks. Thank you so much for watching my YouTube video, and I will see you all next week.